Today's topic is the normal curve. So let's go ahead and get started. And here's the objectives. We're going to start by talking a little bit about the basics of probability density curves and how they can be used to describe a population. And then we'll introduce the normal curve and discuss how that can be used to describe a normal population. We're going to revisit the concept of z-scores, which we covered in an earlier class, and look at ways of finding areas under a normal curve. And we'll wrap up by looking at how to find the value from a normal distribution corresponding to a given proportion. So to get started, we want to revisit the idea of a probability density curve, which we've alluded to a little bit in the past, but we're going to explore that in a lot more detail today. So this is a histogram that we created from an example that we covered in class in section 2.2, back when we first introduced histograms as a way of graphically representing a frequency distribution. So the figure here presents a relative frequency histogram for the particulate emissions of a sample of 65 vehicles. And again, I encourage you to go back and review the notes from section 2.2 to see the example where this histogram was constructed. Now, let's assume that maybe we had information not just on the 65 vehicles, but we had information on the entire population, which contains millions of vehicles. And let's say that we had access to the entire population, and we decided to make a histogram based not off of just the 65 vehicles, but the entire population of millions. Now, because the population contains so many vehicles, the resulting histogram would have a lot more rectangles, right? In the one we created here with 65 vehicles, we have just 1, 2, 3, 4, 5, 6, 7 rectangles, right? But if we're dealing with millions of vehicles, because there's so many, we would have to have a lot more rectangles, and the rectangles would have to be extremely narrow. And so the result would look something like this one at the bottom of your screen. Because the rectangles are so numerous and so narrow, then the sharp edges kind of start to blur, right? And the histogram does not look very much like a series of rectangles, but it looks more like a smooth curve. And in fact, we could draw a curve on top of the histogram, and it would fit the histogram quite well, as you can see from the diagram there. So the curve here that's used to describe the distribution of this variable, we refer to that as the probability density curve of the random variable. Okay? So any population can have a probability density curve. The histogram, typically, a histogram is based off of a sample, and a histogram can give us a rough idea of what shape the density curve is, right? But the density curve itself would be the shape that you would observe if you were able to create a histogram from the entire population, okay? Now, this probability density curve has certain applications that are quite useful. Specifically, the density curve tells us what proportion of the population falls within a given interval. And there's actually two interpretations that we could, if we look at a specific area under a probability density curve between any two values, let's say values A and B, this area can be interpreted in two different ways. So in this diagram, you see the shaded blue area, right? That is the area that falls between the values 3 and 4. This area is equal to the proportion of the population with values between 3 and 4. Or alternately, it represents the probability that a randomly selected value from the population is between 3 and 4. So there's two ways of interpreting that area. We can interpret it either as a proportion or as a probability. Either way, what this indicates is that density curves are quite useful because if we can find these specific areas under the curve, we can use that area to solve certain applications relating to populations, right? Specifically finding either a proportion or a probability within an interval. Now, other properties of density curves. For any probability density curve, the total area under the curve is equal to 1. And this is just because the area represents the entire population, right? If we randomly select a value from a population, right, the probability of getting a number from that population is equal to 1, right? Where that's guaranteed to happen. And so that is why, right, because the area under a curve represents a probability, then it would make sense that the total area under the curve would equal 1, right, because it represents the entire population. Now, density curves can come in many different shapes. And it's not really practical to have a method for finding a specific area under any probability density curve. However, there are many important statistical procedures that can be carried out using only one type of probability density curve, which is called a normal curve. So in this section, we're going to focus our attention specifically on the normal curve and explore how to use that for certain applications. And this is one of the most important density curves in all of statistics. And throughout the rest of this class, we'll be using this density curve in a number of important applications. So it's very important that we really get a clear understanding of it. So this diagram illustrates what a typical normal curve looks like. As you can see, it's symmetric. It looks kind of like a bell, so sometimes it's referred to as a bell curve. It has a single mode, which is the highest peak there, and that mode is right in the middle. And because the curve is perfectly symmetric, that means the median is also right in the middle. So the mode and the median and the mean are all the same, right? Because there's no skew causing the mean to move to the right or to the left. It's a perfectly balanced density curve. A population that is represented by a normal curve is said to be normally distributed or to have a normal distribution. Now, there are lots of different normal curves. All normal curves exhibit the characteristic bell shape. They're all symmetric. They all have that peak right in the middle. But the way they differ from each other is that they can be kind of tall, skinny, or short and spread out, right? All of these things can happen, and the curve can still maintain its characteristic bell shape. A normal curve is defined by its mean and its standard deviation, right? We discussed earlier in the class how a random variable can have a mean and a standard deviation, and a normal curve is one way of representing a random variable, right? Which means that normal curve will have a mean and a standard deviation. The mean is always is the number that the curve is centered over, right? Because the curve is symmetric, that means the mean is going to fall right in the middle, which happens to be right underneath the peak of the curve as well, right? And the standard deviation is a number that dictates how spread out the normal curve is, okay? So the normal curve is wide and flat when the population standard deviation is large, and it's tall and narrow when the population standard deviation is small. And then it's also, again, just noting that the mean and the median of a normal distribution are both equal to the mode. If you recall from our section in chapter 3 about measures of center, that's where we discussed the mean, the median, and the mode, right? The median is simply defined as the number in the middle. And because the normal curve is symmetric, that's just going to fall right in the center. And the mean will fall right there as well, right? Because there is no imbalance or skew in the normal curve that pushes the mean to one side or the other. The mode is defined as the number that occurs the most frequently. And the height of the curve indicates the frequency, right? So it would make sense that the tallest peak would correspond to the mode. So the mean, the median, and the mode are all equal for a population that is normally distributed. In this diagram down at the bottom of the screen, we see an illustration about how normal curves can differ, right? In the diagram on the left, we have two normal curves that have the same mean, but different standard deviations. They have the same mean because they're both centered over the same number, which is the number 0, right? They both have means of 0. But the curve illustrated by the solid line is skinnier than the one illustrated by the dotted line, right? The dotted line curve is wider, so it has a larger standard deviation. Specifically, the dotted line curve has a standard deviation of 2. The solid line curve has a standard deviation of 1. The diagram on the right side of the screen, we have two normal curves that have the same standard deviation but different means. The standard deviation is the same because the curves are both the same width, right? They both have standard deviations of 1. But the solid line curve has a mean of 0, and the dotted line curve has a mean of 5. And again, we know that because those are the numbers that the curves are centered over, okay? The normal distribution follows the empirical rule, which we covered earlier in the class, right? We said the empirical rule specifically applies to distributions, that are bell-shaped, right? And we didn't use the language of the normal distribution back then, but essentially that's what we were referring to, right? A data set that is represented by a bell-shaped histogram is a normally distributed population, and it follows the empirical rule. So just to review that, the empirical rule states that for any data set that is normally distributed, you would expect about 68% of the data to fall within one standard deviation of the mean, and you would expect about 95% of the data to fall within 2 standard deviations of the mean. And then previously we said that you'd expect all or almost all the data to fall within 3 standard deviations of the mean. Officially, that's usually the official percentage put on that is typically 99.7%, which again is very close to 100%. Now, let's talk a little bit about this idea of standardization. Now, our goal is to be able to use a normal curve to solve applications, right? Which means the way that's done is through, we need to be able to identify specific areas underneath a normal curve so that we can use those areas to identify either a probability or a proportion, right? Based off of the concept we discussed earlier about the application of an area under the curve, right? Under any density curve. The problem is, right, that normal curves, there's not just one normal curve, right? There's lots of normal curves because a normal curve can be centered over any number for the mean, or it can be centered over any number for the standard deviation, right? So that makes it hard to set up a kind of a simple method for finding the area under any normal curve. So instead, what we'll do is we'll focus our attention on one specific normal curve. This specific normal curve is called the standard normal curve. And actually, I'm going to go forward one more slide, and we'll come back to that previous slide. But this is what the standard normal curve looks like. Okay, the standard normal, well, I mean, it looks like a typical bell-shaped curve, right? But the specific characteristics of a standard normal curve is that it has a mean of 0 and a standard deviation of 1. Okay. Now, if you recall, back in chapter 3, in the section that we covered on measures of position, we talked briefly about the z-score. The z-score is a number that tells us how many standard deviations away from the mean a particular value falls, right? So a z-score of 1 means that a particular data value is exactly 1 standard deviation above the mean. A z-score of negative 1.5 means a particular data value is exactly 1.5 standard deviations below the mean, right? Now at the top of the screen on the right there, you see the standard normal curve, which has a mean of 0 and a standard deviation of 1. This curve, really what it is simply a curve representing the distribution of all z-scores, right? So if we have a mean of 0 and a standard deviation of 1, and I specifically pick the data value 1, right? Well, that value is going to have a z-score of 1, right? Because if the mean is 0, right, then 1 standard deviation above the mean would just be 0 plus 1, or 1, right? This is 2 standard deviations above the mean, and this is 3 standard deviations above the mean, right? So in other words, what we have is we actually have a pretty simple way of taking any normal curve, right, and converting that normal curve into the standard normal curve. At the bottom of your screen here, we have a normal curve which represents the distribution of women's heights, right? And the data we're given is that the mean height of women is 64 inches with a standard deviation of 3 inches, right? And so let's consider a woman whose height is 67 inches, right? Well, 67 inches is above the mean, right over here somewhere. And I could convert that 67 into a z-score by using the z-score formula right here, which we introduced back in chapter 3, right? Z equals x minus mu over sigma. And I make that conversion by just taking the x value, subtracting the mean of 64, dividing by the standard deviation of 3, and I get 1, right? So the data value 67 on this normal curve at the bottom corresponds to the data value 1 on the standard normal curve, right? And so because it's so easy to convert a data value to a z-score, which basically allows us to convert any normal curve into the standard normal curve, then we really only have to worry about fully characterizing the standard curve, since we then have a way of converting values to the standard curve. So what we're going to do is we're going to look at the typical ways that we can find specific areas under the standard normal curve. And one of the typical ways of doing that is using a table, which is located in the appendix of your book, but you can also find areas under a normal curve using your TI-84 calculator. So we'll kind of look at both methods. And then we'll look at an application where this kind of a typical application problem. involving a normal curve. But before we get there, let's just, we've already looked at this. Let's discuss how to use a table to find areas under a normal curve. So the table for finding areas under the normal curve is located in the appendix of your textbook. If you have the physical copy of the textbook, you can just flip to the back and it's there. If you're relying on the electronic version, one of the easiest ways to access it is to open up a homework assignment in Connect Math. And over on the right side of the screen, there's a series of buttons. And if you click the one labeled Tables, it will just give you a PDF of the appendix. And that's how we've already done that to find the table for the binomial probability, right? We've covered that. The standard normal curve table is in that same document. It's just the second table, table A2. This slide gives a bit of an illustration of what that table looks like. It's actually a 2-page document. So this table right here, or this slide just shows you a brief snapshot of the top of the first page. Okay. The table may be used to find the area to the left of a given z-score. Okay. So what you observe is that the column on the far left of the table is labeled z. And this gives z-scores rounded out to 1 decimal place. And then up here at the top of the table, we see a row with these numbers 0.00, 0.01, 0.02, and so on. That represents the z-score, the second decimal place of the z-score. Okay. And then the numbers in the main body of the table right here, those are the areas to the left of a specific z-score, right? Let's say that I was asked to find the area to the left of the z-score 0.65. What I would do is I would find 0.6 on the column on the left, and then I would move over here till I'm directly underneath 0.05, right? Because this represents the second decimal place. That's the first decimal place, right? So 0.65 would be this number plus this number. And those combined, right? So I use the second decimal place to find the correct column, the first decimal place to find the correct row. Where they meet is this number 0.7422. And that is the area to the left of the z-score 0.6. Oopsies, I'm sorry, I was wrong. Right, so column, oh no, I'm sorry. Yeah, 0.7422 is the area to the left of the z-score 0.65. Sorry about that. All right, here's a typical step-by-step procedure, right? Find the area to the left of z equals 1.26. I would highly recommend when you're solving these problems is to just go ahead and sketch a normal curve. It doesn't have to be perfect, right? Just a quick hand sketch. And then indicate on your sketch where the z-score sits, right? A positive z-score is always going to sit to the right of the middle, to the right of the mean, right? So just kind of roughly estimate where you expect that to be, and then shade the area that you're asked to find, which is the area to the left. So the area to the left of 1.26. Then consult your table, right? The column on the left gives your z-score out to the first decimal place, right? So the z-score is 1.26. So find 1.2 on the left column, and that's the row you want. And then move across that row to the right until you find the number that's directly underneath the value 0.06, right? Because 0.06 is the second decimal place, right? Basically, the number 1.2 and the number 0.06, if you add them together, you're going to get 1.26, right? So think about it that way. So the second decimal place is used to find the proper column. And where they meet is the number 0.8962. So the area to the left of z equals 1.26 is 0.8962. Okay. Now, the table only directly gives areas to the left, but it can be used to find other areas as well, simply by knowing the geometry of the curve itself. Okay, so let's look at an example of how to use the table to find the area to the right of a given z-score. In this example, we're asked to find the area to the right of z equals negative 0.58. Again, I would highly recommend that you just, for all of these problems, just do a quick sketch of a normal curve and label on that normal curve roughly where you would expect the z-score to be. A negative z-score is always going to fall to the left of the middle, right? Because it represents a data value that is below the mean. And then if you go to your table in the appendix, if you look at the full table in the appendix, you'll see it's divided up into 2 pages. And the first page of the table represents areas corresponding to negative z-scores. And the second page of the table gives you areas corresponding to positive z-scores. So that's how it's divided up. Okay? So in this case, we're going to be using the first page of the table because it's a negative z-score. So once again, we will go to our table, and on the column on the left, we will find negative 0.5, right? Because the z-score is negative 0.58, we just want to find the first decimal place on the left column. The second decimal place is 8, right? So specifically it'll be 0.08, and we use that to find the appropriate column. And where that row and that column meet, we see highlighted in green there the number 0.2810. Now remember, the table only gives areas to the left, right? So that means that if you look at the diagram at the bottom right of your screen, the area 0.2810, that's the area to the left of negative 0.58. But what we've been asked to find is the area to the right. But as we said earlier, the total area under any density curve is equal to 1, right? So if you know the area to the left, we know the area to the left and the area to the right have to add up to equal 1, right? So I can just take the area to the left and subtract this area from 1 to obtain the area to the right. Okay? So if you want to find the area to the right, you have to take that one extra step. And this is why it's really helpful to have a diagram, right, where the area you're trying to find is shaded, just to kind of remind you to take that extra step if the area is to the right. And this is why it's not necessary for the table to specifically show areas to the right, because it's easy to find the right areas from the left areas. Okay? Now, the other possibility is that sometimes you might want to know the area in between two z-scores, right? Instead of just finding the area to the left or to the right of a single z-score, we might want to find the area in between two z-scores. The table can also be used to do this. Again, I would highly recommend doing a sketch. So in this case, we want to find the area that falls between z equals negative 1.45 and z equals 0.42. So we'll sketch a normal curve, and we'll label the points on the normal curve, or we'll label the z-scores, right? A negative z-score falls to the left of the middle, a positive z-score falls to the right. So just kind of indicate where you expect those to be, and then shade the area in between them. Then we'll go back to our table, and we'll use the table to find the area to the left of both the z-scores. Okay. So if we use the table in exactly the way that we did in the previous two examples, we'll find that the area to the left of z equals negative 1.45 is 0.0735. And the area to the left of z equals 0.42 is 0.6628. So here's what we have, right? Over on the right, this is the area that we want to find, right? If we find the area to the left of 0.42, right, that gives us the entire area under the curve to the left of that. But if we take this area and remove the area to the left of negative 1.45, what we'll be left with is the area in between the two values, right? So the way we do that is we take the area to the left of z equals 0.42, and we subtract from that the area to the left of z equals negative 1.45. And what we're left with is the area in between. So essentially what we do is we find the areas to the left of both the z-scores, and we subtract the smaller area from the larger area to find the area in between, right? In this case, so the areas to the left are both obtained from the table, right? 0.6628 is the area to the left of 0.42. 0.0735 is the area to the left of negative 1.45. When I subtract, I'm left with 0.5893. That is the area in between the two z-scores. Okay. Okay, let's look at an example. In this example, it utilizes a normally distributed population, but it's not a standard normal distribution, right? So in this example, we will have to go through the standardization process before we can use the table to find our areas, okay? So here's our example. A study reported that the length of pregnancy from conception to birth is approximately normally distributed with a mean of 272 days and a standard deviation of 9 days. What proportion of pregnancies last less than 259 days? So I would recommend, if you have a piece of paper, just do a quick sketch of a normal curve, draw a bell shape, right? And this time we're dealing with a normal distribution that has a mean of 272, right? So 272 will fall right under the middle of that bell curve. The question is, what proportion of pregnancies last less than 259 days? So that means on your picture, on your paper, you might just kind of roughly indicate where you would expect 259 to fall. It's going to be a little bit to the left of the middle, right? And then on your picture, shade the area to the left of 259. And that is the area that we're trying to find, right? Now, so you should have a picture that shows that shaded area, but we can't quite yet just jump to the table to find the area because the table only works for the standard normal curve. And this is not the standard normal curve, right? So we have to go through one extra step before we can go to the table. And that step is we have to take the data value 259 and convert that to a z-score using the z-score formula, x minus mu over sigma, right? So we take 259, subtract the mean, divide by the standard deviation, and we get negative 1.44. Now we can go to the table and just do exactly what we did in the previous examples, right? Find the area to the left of z equals negative 1.44. find negative 1.4 on the left column, move over that row till we're directly underneath 0.04, and the number we find there is 0.0749. So we conclude that the proportion of pregnancies that last less than 259 days is 0.0749. Okay? Let's do another example, right? Again, same study, right? The mean length of pregnancy from conception to birth is about approximately normally distributed, with a mean of 272 days and a standard deviation of 9 days. This time, what we're asked, what proportion of pregnancies last longer than 280 days? Okay. Again, if you have a piece of paper handy, I would suggest go ahead and just do a quick sketch of a normal distribution. Put 272 right under the middle, and then indicate where 280 would sit, which is a little bit to the right of the middle, right? And this time, because it says longer, that means the area that we're trying to find will be the area to the right of 280, right? So you might shade that area. So again, we have to convert 280 to a z-score before we can use the table. So I take the data value, subtract the mean, and divide by the standard deviation. And I get 0.89 as my z-score. Now I go to my table, right? Find the area to the left by finding 0.8 on the left column, move across that row till I'm directly underneath 0.09. The number there is 0.8133. That's the area to the left, but we want the area to the right. So we'll take 1 minus that value to get 0.1867. So we conclude that the proportion of pregnancies that last longer than 280 days is 0.1867. Okay? Let's look at one more example. This one is finding the area in between two values. A pregnancy is considered full term if it lasts between 252 days and 298 days. What proportion of pregnancies are full term? So, again, it's helpful. In this one, we have the diagram here on the screen. Just go ahead and sketch a normal curve, right? And the normal curve is centered over 272. And then put on that diagram, indicate where 252 and 298 would fall, right? 252 falls to the left of the mean, 298 falls above the mean, and shade the area in between. Now, in order to use the table, both data values have to be converted into z-scores, right? So for both 252 and 298, we subtract the mean, divide by the standard deviation, right? And as you can see, the calculations there on the screen, the z-score for 252 is negative 2.22. The z-score for 298 is positive 2.89. Then we go to the table. We find the area to the left of both z-scores. The area to the left of 2.89 is 0.9981. The area to the left of negative 2.22 is 0.0132. The area in between is found by subtracting the smaller area from the larger area, which leaves us with 0.9849. So the proportion of pregnancies that are full term is 0.9849, or about 98.5% of them. Okay? So that illustrates kind of a typical example of how a normal curve can be used to find either a proportion or a probability by finding the area under the curve. Now, the table is not the only tool you can use to find these areas. Your TI-84 can also be used, and so if you have a TI-84 calculator, these are the instructions for how to find those areas using that, right? Specifically, the command that we would use is called normal CDF. And this command is accessed by pressing the second key followed by the vars key. It's in the distributions menu. Okay. And when you access this command, 4 numbers have to be used as inputs. Okay. The first number you would enter is the lower bound of the area. The second number is the upper bound of the area. Then the last 2 entries are the mean and the standard deviation. So they're entered in that order. Okay. The nice thing about using the normal CDF is that you can type in any number for the mean and any number for the standard deviation. So you don't have to go through the extra step of converting the values to z-scores first, like you do when you're using the table. Okay. So just a simple example, right? Revisiting an example we did earlier in this lecture. Find the area to the left of z equals 1.26. Well, again, I think even in this case, it's helpful to sketch a normal curve, right? Label the point z equals 1.26 and shade the area to the left. Okay. Now, when it comes to inputting values in the calculator, there's some specific, the method we use for the lower endpoint, right, is we plug in this -1e99. It's worth kind of pointing out, right, that when we're shading the area to the left, there's not really a distinct left endpoint. One thing about the normal curve is that it exhibits what we call asymptotic behavior, which means as you look at the tail of the curve, it approaches and gets closer and closer and closer and closer to this horizontal axis. But asymptotic behavior means that it gets closer and closer, but it never ever quite touches, right? So in reality, the curve keeps going to infinity, off to the left and off to the right, right? It doesn't have a distinct endpoint. It just keeps going forever. So in your calculator, instead of putting in infinity, we don't really have a way of inputting infinity into a calculator. So we kind of approximate infinity by putting in either a really big number or a really small number, right? So the left endpoint, we represent that with -1e99, which represents -1 followed by 99 zeros. Okay. So that's what we would put as the lower endpoint. And then the upper endpoint is the distinct value 1.26. Okay. And then because this refers to the standard normal curve, we would put 0 as the mean and 1 as the standard deviation. And then you would run the command and the area should show up on your screen. It's worth mentioning that the area you get from the calculator might be very slightly different from the value that you would get from the table. They should be very, very close, but don't be surprised if you see some very minute differences, and that's primarily due to rounding. The table assumes it gives you areas corresponding to z-scores rounded to exactly 2 decimal places, right? So sometimes there's rounding errors. The calculator would actually be, when there's a difference, the calculator would probably be like actually the more accurate one. But both answers should be very close, right? You shouldn't see any major differences. Let's go back to this example and illustrate how we would use the calculator for this one, right? What proportion of pregnancies last less than 259 days? So, again, we would use the normal CDF command, and again, for the lower endpoint, we would put -1e99, and this time we would put 259 as the upper endpoint, and then 272 as the mean and 9 as the standard deviation, right? We can just type those numbers in directly, so we don't need to convert them to z-scores first. And when you do that, the number that appears is should be about 0.0743. Again, that might be a slight bit different from the number that you get from the chart, but they're very close. What proportion of pregnancies last longer than 280 days, right? This time, because we're finding the area to the right, then 280 is the lower end point, and the upper end point we would approximate positive infinity by typing in 1e99. And again, 272 is the mean and 9 as the standard deviation, and then run the command, and we would get 0.187 as the result. Okay. Lastly, what proportion of pregnancies are full term? In this case, we would run normal CDF, and in this case, we would want to put 252 as the lower endpoint and 298 as the upper endpoint, right? So in this case, we have a very distinct lower and upper endpoint. 272 is the mean, 9 as the standard deviation, and we should get about 0.9849 as the result. So that's how the normal CDF command. Please feel free to reach out to me if you are having trouble with your calculator or if there's any confusion, and I would be happy to go over that in a bit more detail with you. Okay, in the examples we've looked at so far, what we've done is we have used a z-score to find an area, right? Like in the application example, relating to the length of a pregnancy, we started with a data value. We converted that data value into a z-score, used that z-score to find an area. But there are many problems that require us to go in the reverse direction. That is, if we might be given an area, and then we need to find the z-score that corresponds to that area under the standard normal curve. And then we may need to take that z-score and convert it into an actual data value, right? So this is going through the process backwards, starting with an area, finding a data value, instead of starting with a data value, finding an area. So let's go over how we might do that, right? First of all, once we find the z-score corresponding to a specific area, we are going to want to convert that back to an x value or a data value, right? Now we can use the z-score formula to do that, but this time z is a given value and we're trying to find x, right? So what we can do is we can take the z-score formula and we can algebraically solve it for x. If we do that, we get x equals the mean plus the product of the z-score times the standard deviation. X equals mu plus z times sigma. So that is the formula that we use to convert a z-score to a data value, right? So like for example, say that heights in a group of men are normally distributed with a mean of 69 inches and a standard deviation of 3 inches. Let's find the height whose z-score is 0.6 and interpret this result. Okay. We want the height with a z-score of 0.6, right? So we take this formula, right? Plug in the mean, the z-score, the standard deviation, and we get 70.8. We would interpret this by saying that a man 70.8 inches tall has a height 0.6 standard deviations above the mean. So here is the step-by-step procedure that we would follow for finding a value from a normal distribution that has a given area, right? So again, I would just always recommend going ahead and sketching the normal curve. The mean should be a given value, but in these examples, the area is what's given, not the value, the data value itself, right? So you might just indicate roughly where the data value falls. We don't know the numerical value of it yet, but we should know roughly where it falls, and then shade the area that's given in the problem. If the area is on the right, we should subtract it from 1 to get the area on the left. And this is simply because if we're using the table only gives areas to the left, right? So we need to know the area on the left. Then we can go to the table A2, but we'll use it in a slightly different way this time. Previously, right, we had a z-score, and we used the z-score to find an area. But this time we're looking in the main body of the table to try to find the area closest to the given area. And then we find the z-score corresponding to that area. Once we find that z-score, convert it into an x value using this formula right here, x equals mu plus z times sigma. So here's an example that illustrates that process. Mensa is an organization whose membership is limited to people whose IQ is in the top 2% of the population. Assume that scores on an IQ test are normally distributed with a mean of 100 and a standard deviation of 15. What is the minimum score needed to qualify for membership in Mensa? So it would be helpful to sketch a normal distribution, right? This represents the distribution of all IQ scores. And my normal distribution will be centered over 100, since it says normally distributed with a mean of 100, has a standard deviation of 15, right? It specifically says that Mensa is an organization whose membership is limited to people whose IQ is in the top 2%, right? So we'll just kind of put a value of x here. Our ultimate goal is to determine what x is. The area to the right of x is 0.02, because that represents the 2% of the population who qualify for Mensa, right? They have IQs that are larger than x, sorry. The area to the left of x is 0.98, 1 minus 0.02. That represents the 98% of people who don't qualify for Mensa, right? So now, once we've identified the area to the left, then we go to the table. Let me just flip over there real quick. And this table looking for the area that's closest to 0.9798. It's going to be, or sorry, it's closest to 0.98. My apologies. Okay. So if we do a quick scan, we should find that, right here. Let me just indicate that. This is the number that is closest to 0.98. Rarely will you find the exact area, so you just find the area that's closest, right? And that corresponds to a z-score of 2.05, right? 2.0 over here, 5 up here. Flip back over to my PowerPoint here. All right, z-score of 2.05, and then we want to convert that z-score into an x value using the formula x equals mu plus z times sigma, right? Which equals 2.05, equals 100 plus the product of 2.05 times 15, and we get 130.75. IQ scores are generally whole numbers, so it makes sense to round this. We'll round it to 131, right? So in order to qualify for Mensa, you have to have an IQ score of at least 131. Finally, let's just go over how we can do the same thing using the TI-84, right? I've seen this slide already, so let's just kind of jump ahead. The command that we would want to use on the calculator for this is the inverse norm command. Again, also from the distribution menu, it's right underneath the normal CDF command, which we looked at earlier. What this command does is it returns the value from the normal population with a given area to its left. Okay? So the input has to be the area to the left, and then the second and third values that we input are the mean and the standard deviation. So if we were to use that for our Mensa example, we would access the inverse norm command, and the first number we would input is 0.98, since that's the area to the left of the given value, or that's the given area to the left, right? The next number we would input is 100, because that's the mean of my normal curve. The third number I would input is 15, since that's the standard deviation. Then you just run the command and round to the nearest whole number, which again rounds to 131. So that's an even simpler way, really. Once you practice getting familiar with that command, it's actually simpler to do it this way than to use the chart method, although both methods work fine. So that covers the basics of how to use a normal curve for certain applications, right? We've discussed how to use a density curve to find a population, how to find areas under a normal curve, and find values from a population corresponding to areas under a normal curve. So that's it for this lecture. Thank you for watching.